So for my calculation video and my project as a whole, I'm focusing on the James Webb Space Telescope, and I have to pick an instrument from that, so I chose the NIRISS, which is a huge, very long acronym, standing for Near Infrared Imager and Slitless Spectrograph, which sounds super complicated, but for our purposes, for this calculation video, we're going to be doing something super straightforward and something we've done in class with some exoplanet studies. So we're going to be choosing an exoplanet, a real one, not some hypothetical situation. It's exoplanet WASP-96b, and we know from the naming of exoplanets that the star system is WASP-96, and this planet is B, so we can say that. So what we know about WASP-96b, it was observed before JWST, which I think it was discovered in 2012. It's a mere 1,100 light years away from Earth, which is just a hop, skip, and a jump away. And it orbits a G-class star, WASP-96, as we said, at about 0.05 AU. And that's important. It's a G-class star, which means it's a sun-like star. So we're going to be doing a lot of approximations in this video to say, oh, this is akin to our solar system, and it's going to be filling in a lot of gaps of, we can compare this system to the likes of our own solar system with a sun-like star. So that's really helpful. And exoplanet WASP-96b was observed by JWST for 6 hours, and it was observed using the transit method, which if we go right over here to this light curve is something we've definitely talked about in class. Now, this is a period of about 6 hours, and you can see the telltale sign of a transiting exoplanet right here from this huge, it's exaggerated, but huge dip in flux, and this dip in flux is approximately 1.5%. which doesn't seem like so much, but especially exaggerated here, and when you consider how large this star must be and how dim the planet is, that's huge, and that's really fun. So we can see from this light curve a very important thing, that we have our value of delta F, or the change in flux, being equal to 1.5%, or if you'd like decimals, 0.015. Now that's super important, and we can do a lot with this. So if we have this, let's add it to our list of givens. And let's continue. So this transit light curve is basically just summed up in this very crude model right down here. That's not to scale and not to color either. But this is a model of WASP-96b transiting in its orbit around the star here. And right here, when this planet comes right in front of the star, we can see the dimming of the star's light, and that's what this flux over time thing is measuring, which is great. So now we have that, and what can we do with this? Well, there's a couple of things we can do from something we know, which is a change in flux. And that's find the radius of WASP-96b. So if we need to find the radius of an exoplanet, great, we know how to do this. So there's a couple of ratios we can set up. And that, as an equation, we know, is that the change in flux is equal to the area of the planet over the area of the star. And what's area? We don't know anything. Yes, we do. We have some radius values. And if I read from the NASA Planetary Fact Sheet, or Exoplanetary Fact Sheet, we know the value, we know the radius value of WASP-96. And that happens to be R equals about 1.05 times the radius of the sun, which approximately is equal to 7.31 times 10 to the 8th meters, which is a great value. Now from area, we know our area of a sphere is pi r squared, so we can change this ratio into pi r of the planet squared, pi r of the star squared. And great, we've identified our knowns and we've identified our unknowns. We can cancel out these pi's for easy sake. We could say the change in flux is equal to r of the planet squared over r of the star squared. When we rearrange this, because now our unknown is r of the planet, we can rearrange this to find the equation r of the planet is equal to r star times the square root of the change in flux. So wonderful, we can make our super easy calculation now and solve for the radius of WASP-96b. And once we plug in our known values, that comes out to be something around the order of 8.95 times 10 to the 7th meters. And that's a great value. That's also an approximation. I should have included some squiggly equal sign there because this is an approximation. But it gets us pretty darn close to the actual number, which I wrote here on the board as a revealing magic trick. And actually got it wrong. that should be a 7. Which gets us pretty darn close. We have 8.95 times 10 to the 7th meters and 8.39 times 10 to the 7th meters as our actual measured by Webb and by NASA. So this approximation gets us pretty close. It's a pretty straightforward calculation to get the radius. And now the reflection question, and this kind of departs a little bit from JWST's goal, because this is known and done well before JWST. But given that WASP-96b orbits a sun-like star once every 3.4 Earth days, which if we write that out, we can do some conversions here. So given that its period equals 3.4 Earth days, how can we find the semi-major axis of WASP-96b? Now it's a reflection question, so we'll just walk through it super quickly and then you can calculate that to get it. We know Kepler's third law is that p squared is proportional to a cubed, and in that case, if we're working in years in AU, and we're assuming a sun-like solar system model, we can just equate p squared equals a cubed. Again, that's why this G-class star is super important, so we can make this approximation. So if we do that, and we say Kepler's third gets us this far, then we can say, oh, if we want to solve for A, let's get you there, and do that. And with the P that's known, it is in days, and if we can get it in years, that would be wonderful. You just divide 3.4 by 365. We can find out what that is. And as a reflection question and for a fun calculation, you can solve for that A. And that's pretty much it. So we now know the radius, approximately, of WASP-96b, and you know more about JWST's NIRISS. Thank you.